Welcome everybody to the Quantum VC seminar. It looks like we've got a very good turnout, online at least. So today we're going to be hearing from Andrew MacRae, who's at the University of Victoria. He's our resident quantum optics person in the department and runs a very popular lab, drawing in people from, well, all over the undergraduate program here. So sort of continuing the theme of the past couple of talks, we're going to be hearing about atom-based quantum memories and sources of telecom integration. Andrew started at the University of Calgary at the Institute for Quantum Information Science, and then continued as a postdoc at the University of California at Berkeley. And we're very glad to have him here. So without further ado, take it away.
All right. So people here. Is that okay? First off, thank you for the invitation to speak here, and thanks for everybody here. Just counting the thousands of people in this room, not the few, for the invitation to speak about this stuff. I want to talk about some of the things that we're working on at UVic here to make some progress towards this ambitious goal of a quantum internet. The door here. So the talk is basically split into two. Where the first part of the talk, I'll just talk about some of the basics of what is meant by a quantum internet and a quantum network, which might be somewhat jargony, and some of it was already talked about in a previous seminar, so it would be kind of colloquial. And then for the second part of the talk, we'll talk about some of the particular things we're working on UVic in order to sort of play a small part in realizing this very ambitious goal. So part one, using my phone, full PowerPoint, there we are. The quantum internet with a question mark, because there are some questions that come up when you're talking about something like the quantum internet. So I was told by my English 11 teacher that you should not define a word by saying what it's not, but I'm disobeying that. I'll say right away that the quantum internet is not the classical internet, but with the word quantum before it. So a nice place to start is, what do I mean when I say the internet? Like a lot of people picture either the application layer or a bunch of fibers, and really it's everything, right? So the internet itself is infrastructure, and which is devices and links between places. So that's what we call a physical network, but also protocols, and one without the other can't really accomplish anything, right? So we need to transmit information from A to B. That's what the internet is doing in the form of bits, which can be ones and zeros, or highs and lows, or frequency 1 or frequency 2. It's very abstract. But we need a protocol to say how we're going to route these packets, so TCP/IP, as well as encodings. That all has to be part of the internet as well. And when we talk about the internet, it's important to note that it's not just the infrastructure. It's also the ideas and the protocols behind it that allow universal communication. So the quantum internet, I'll start by saying what I said I wasn't going to say, and just put quantum in front of everything. It is a way of transmitting information between 2 points, right? So instead of a network, we need a quantum network. Instead of devices, we need quantum devices and quantum protocols that are the analogies to it won't actually be TCP/IP and everything. But we're going to transmit quantum bits, and there's the big difference there, where we're not actually trying to transmit our information by ones and zeros. It's qubits, and people like to say, it's a 1 and a 0 in superposition, but really it's, to think about it more as an experimentalist at least, is it's part of just a 2-dimensional kind of Hilbert space. It's a subspace that we can play with, and that subspace can carry information. And the analogies kind of break down here when we want to start routing information. So let's think about how I might want to. I'm sitting here with some colleagues in Victoria. How I might want to talk to people in SFU or UBC. How am I going to encode that information? I'm not really sending the information through wires. I have a cartoon here. What's going on? I have a qubit here, and what this supposed quantum internet is going to do is it's going to help establish entanglement between myself and say the people at SFU over there. And once we've established that entanglement, we're sharing part of the same wave function, kind of non-locally. We're going to do measurements, unitary operations, and kind of classical communication in order to transmit that information. So it's not like we have a pipeline where we're sending bits. We're establishing this non-local wave function over, any arbitrary distance, performing measurements and using those measurements to transmit information. Okay, so it's very different. I don't like to think about the quantum internet as an internet with quantum. It's a totally different mechanism. And I think a better distribution, or a better, definition would be a set of technologies by which we can establish entanglement over long distances in a controllable way. So it's a device or a set of devices and protocols that will allow me to establish a shared part of an entangled state with any other node on this network on the planet. And I think that's a more useful way of thinking about it. Okay, so there's a quantum elephant in the room here. Is it too soon for this? By the way, this is one of two generative AI pictures I used in here. And this is the rule of thumb for this talk. Anything that looks photorealistic is made by AI. Anything that looks good is made by others. And anything that looked like it was made by a sixth grader was made by yours truly. So not an artist, but the quantum elephant in the room here is, isn't it presumptuous to make a quantum internet before we have fully functional quantum computers? I think everybody would agree that we're not really there yet with quantum computers. So it seems like an awful stretch to say, oh, we have these quantum computers, let's make a quantum internet to control them. And I would argue that this is not the case. So this is not an analogy. This is not an analogy to how we made the classical internet, right? So digital computers came out in the late 40s and in the early 50s, and then it was several decades or 2 decades before the ARPANET came out and started connecting these computers. And I think it is not correct to think about the purpose of this quantum network and quantum internet to connect quantum computers. It's much more than that. And furthermore, if we never get quantum computers, I think we will get quantum computers that are, universal, and we can use them for everything, have many logical qubits. Sure, we will. But suppose we don't. I would argue that it is still useful to have this quantum internet, right? So one of the things that was talked about, not last seminar, but 2 seminars ago by Thomas Genowin was ways of distributing quantum keys through a satellite-based network. So it's already been kind of demonstrated. We'll go into a bit more detail a bit later, but the basic idea is that we can establish a link between 2 nodes and transmit information in such a way through quantum states that the statistics are measurably altered when you are transmitting information and someone else is also measuring that. So basically, even if someone is making a weak measurement between channel A and channel B, this will come out in the statistics really quickly, especially if we have a high key rate. So that's already being used. I'll talk about some of the advances in recent years. That's already here. And I think the first version of what we call the quantum internet will do nothing but distribute quantum keys and help encryption. But there's also equally exciting, maybe even more exciting sensing applications that take advantage of an entanglement fundamentally and allow us to do things that we just cannot do with classical computers. So one of them is a cartoon of phase synchronization and clock synchronization, or phase estimation and clock synchronization over a distributed network. And I heard a really, my favorite application is extending the baseline, a very long baseline interferometers. But unfortunately, I was talked about in great detail in the last seminar, so I was scooped in that, but I was scooped by the person who wrote the paper, so I can't really argue. But the point that I want to stress here is we can do these things even if we do not have quantum computers ever. There's applications that will pop up in the absence of quantum computers. And suppose we do get quantum computers, even better. Now we can actually link them and have distributed quantum computing where you can securely transmit the results of your computation or make use of two quasi-powerful quantum computers to link them up and do it in computationally distributed way. So this is a view about how some of these architectures might work. So it is not too soon, I think, to start talking about quantum networking. And there's some applications that will happen right away. So I just want to talk, in this part of the talk about what some of the key protocols, nodes, and technologies are that will be required to make this this a reality, right? So the three that I want to come about are the nodes on our network, the quantum channel that's going to distribute the quantum information, as well as a new challenge that is not really fundamentally challenging in the classical case, but is, I think, the bottleneck nowadays of long distance quantum communication, the limitation imposed on us fundamentally by physics that we cannot just simply amplify a state in a trivial way, an arbitrary quantum state. So I just want to go through these three one by one before kind of getting into the how we're trying to solve them. So first of all, the building blocks of these quantum nodes here. What we're going to do is we're going to start with a Bell source, a source of Bell states. So if we recall, a Bell state is a superposition of 0, 1 plus or minus 1, 0, or 0, 0 plus or minus 1, 1. It's a four-state basis that are going to be the kind of the building blocks of all our protocols when we're distributing entanglement or establishing entanglement between two nodes. We're going to do it kind of from this primordial clay here of these Bell states, which was working. But I'll give it a shot. And these qubits can be arbitrary. The important note is, many of you, this is the quantum BC seminar, so many of you are very familiar with these terminologies here. But when I write an entangled state like this with two states, 0, 1, 1, 0, these two states can be completely spatially separated, right? They can be separated by 6,000 kilometers, and as they will be in a quantum network, and the state remains entangled. So we need a way of making these Bell states, and when we're doing so optically, a very convenient basis is that of polarization, right? Okay, so slowing it down a bit and going into a bit more detail, I think the most basic application of this or implementation of this is using the fact that light is transverse. Therefore, there's 2 degrees of freedom. There's a 2-dimensional subspace, like wiggling this way or this way. This forms a very nice Hilbert space for logical 1 and logical 0. Bell state, say, psi plus, might look like this. Very easy to encode. And what I don't have here, it's also very easy to perform operations, like poly X, Y, and Z. You can do so by rotating something we call a wavelength. So it's very easy to perform operations on these states. And it's well known for several decades now how to actually make them. Making them is one thing. Knowing which state we have, measuring them is another thing altogether. So we're going to need not only a source in these nodes, we're going to need a way to measure what state we have. Bell state measurement. This is kind of a picture of how this might be done optically with just basic linear optics. There's a beam splitter here. That beam splitter is basically mixing the two modes. And then it's followed by 2 polarizing beam splitters, which tells us whether or not our light is horizontal or vertical. And we can condition on getting a single click in that top pair here and a single click in the bottom pair. And based on the statistic there, we can tell whether or not we have a particular Bell state. Now, another elephant in the room here is that this is not a deterministic measurement in the sense that half of the time it will fail with linear optics. It's impossible to differentiate with linear optics. If there's a theorem, we cannot differentiate between all possible Bell states with linear optics alone. And this is a huge limitation. So what that means is that our measurement is going to fail half the time. Not great. 2 ways of doing this. One of them is to have a high source rate so that if it does fail, we just start again. And that's kind of the current approach. But I should say if there are nonlinearities allowed, you can make deterministic Bell state measurements. And this is kind of one of the big pushes now. It turns out it's very difficult, but not impossible to have giant nonlinearities to the point where single photons can experience them. There's been a lot of work done on giant phase nonlinearities, for example. But we need an optical nonlinearity if we're doing this optical Bell state measurement, or else it's going to fail at least half the time. So that's our measurement. That sounded challenging, but that's easy compared to the next couple. So we're also going to need a quantum memory. So as we're distributing entanglement through our modes, we're going to need to be able to hang on to a state, say R half of the Bell state, and reliably map it into usually a set of atoms or a cavity in such a way that it preserves its quantum state, and at some later time, map it back out, right? And these as well, there's different protocols for doing this. It can be so-called heralded, where it probabilistically works, but you know when, or deterministic, where it's all but certain that it works, say 99% of the time. That would be better, but a key parameter here is the probability of it working, which we call the efficiency. I'll speak on that a bit later. The fidelity, so you're going to get a state in, you're hoping the state you retrieve is the same as the state you get in. That's never going to be perfect. Because an optical mode is a particular spatial temporal profile, and there's losses that can, instead of having a pure state, you have a density matrix with a small backing component. So the fidelity, this overlap between the states, is a huge parameter here, as well as the coherence time. How long can you hang on to this? So I've heard optical drives, classical optical drives, have a good storage life, a shelf life of 10 or 20 years. I've heard different numbers here before they're demagnetized, they don't work anymore. 10 or 20 milliseconds would be great for quantum memory. We don't need super long storage time because light travels so fast. We just need to hold on to it as long as the entanglement takes to get established. After that, we can kind of try again and operate at a very high rate. I should say that there are some quantum memories that are going out into seconds or some claims to even minutes, but with very, very low efficiency. So the final thing, which I think is kind of the final boss, the ultimate challenge, is to have full error correction. So as light propagates through a fiber or goes through stuff, things can happen. You can get something called birefringence, where you get a relative phase shift between the horizontal and vertical components. And that introduces phase, it leads to it can turn a psi plus into a psi minus. There's also loss. And we need a way of mitigating these errors that are naturally going to accumulate as we propagate our quantum states through fibers. And there's many protocols for doing this, error correcting codes, so-called entanglement purification. Both of these are very similar protocols. You start with, say, n copies of a Bell state, and entanglement distillation or purification, we do a selective measurement and come up with n less than n copies of a higher fidelity state. Detection is along a similar vein. What we want, first of all, is just error detection to tell whether or not there's a bit flip error, the probabilistic event, or phase error or loss, and just put on a red light and we give a signal to resend. So nothing is going to work perfect, and we're just going to have to develop protocols for making this network work in a reliable way, despite these losses. Okay, so those are the building blocks of the nodes. Now we have to talk about the actual quantum channel, right? So when we actually have this channel, we're going to have a few kind of key protocols that I want to go through here. So there is two key kind of things that we need to go over. And again, this is very colloquial, but we'll kind of go over in some detail how these work. We're getting into the nitty gritty. And the two of them are teleportation and entanglement distribution. They're very related protocols. And the whole idea is making use of these this primordial clay Bell states that we had. Alice, or A and B, want to transmit information. The goal here, I'm going to use this laser pointer. The goal of this protocol is that we have some state psi, and it needs to be teleported to Bob. We need to transmit it to Bob some way, right? So remember the infrastructure of a quantum network is not that we are sending kind of bits through wires. We're going to make use of shared entanglement. And the way this one works here is that we're going to have some Bell source that's going to non-locally distribute a Bell state between Alice and Bob. Now, Alice on her side has this state psi, which she wants to teleport to Bob. I think someone wants to get in. The way she's going to do that is do a Bell state measurement, but not on the Bell state. She's going to take her side, her half of the Bell state. Bob is still holding his side in his own quantum memory here, and do a Bell state measurement on that half of the state. Now, if you have a very big piece of paper and a little bit of patience, you can write out the state that is formed between this Alice's half of the Bell state and her arbitrary state psi, alpha 0 plus beta 1, alpha H plus beta V, and it's some big tensor product here. But importantly, it's a tensor product between Bell state 1, Bell state 2, Bell state 3, and Bell state 4. And each of these states is accompanied by a state which is a simple unitary operation, poly Z, poly X, or a identity away from this. So what Alice is going to do is probabilistically, probability 25%, going to measure either one of these Bell states, psi A, psi B, phi A, phi B, and she's going to communicate classically to Bob and tell Bob what unitary operation to perform. In doing so, that unitary operation is going to be performed over in Bob's channel, and therefore faithfully represent the state size. So it's kind of a neat way of teleporting information, a single quantum state, from Alice to Bob, non-locally sharing this state psi plus, or phi plus in this case. A related protocol, which we're going to use quite a bit, is entanglement distribution. So the idea here is Alice and Bob, they're sharing entanglement, perhaps with another party here. So Alice and Chuck and Bob each share a Bell state, and therefore there's an entangled state between Alice and Chuck and Bob. And the goal is that Alice and Bob want to distribute that entanglement between each other. And of course, they can go on to more and more nodes. So how are they going to do that? Similar idea. You take maybe even a bigger piece of paper and write out the basis that Chuck sees formed between the two halves of this Bell state that they're sharing, while Alice and Bob are each holding their Bell state in their own quantum memories. And Chuck is going to do a Bell state measurement, all right, with each half of that Bell state. With probability 25%, Bob will have, and Alice will share either of the Bell states, which can then be transformed or just used as is. So this way, entanglement between Alice and Chuck and Bob is distributed from Alice to Bob. And this can be done in a chained way to leapfrog entanglement across a network. The neat thing about this is it's done kind of without Alice and Bob ever directly interacting. Right? So that's the kind of the protocol. We've done the nodes. The last thing is the actual channel, how we're going to send them. And previously, we've heard about the potential for satellites to distribute quantum information. Very cool application. We'll be going with old-fashioned optical fibers here. So I found a few pictures of what a fiber looks like before it is born. So the top left here is what's called an optical preform, basically a big piece of glass, silica. And that silica, very pure silica, is turned into an optical fiber. So if anybody has played around with an optical fiber, it's surprising to think that bendy, stringy thing that you're actually playing with is actually a piece of glass. And you don't want to bend it too much or it'll break, but you can bend it quite a bit. And glass, it turns out, behaves quite differently if it's a very, very small radius. And if you ever want some visual meditation, I recommend you go into a YouTube channel and watch a fiber being pulled, because it's quite fascinating. You have this optical preform here. It's put into a tower and heated up, so it's molten. And what happens is a droplet forms, and that droplet, as it's melting, just falls under its own weight. And that falling string that it leaves behind is the optical fiber. It goes through various drying procedures in such a way to not introduce any impurities. And there's a very small picture here, I apologize, about a drawing tower that is distributing that. And as that thing is falling at a given rate, it goes into a form which is wound around a set of pulleys, and it goes onto a big spool. So it's really you can make this kilometers long piece of glass that is going to be the channel for communication. And the loss in this is so low that you can string together many of these fibers and have long networks. So here's a picture of Maria. I think I'm probably saying that incorrectly. It's kind of Spanish word for tide. That links Huntington Beach in the US to Bilbao in Spain. And it's over 6,500 kilometers of optical fiber that goes through the ocean here. And you get very, very high bandwidth, like over a terabit per second in these optical fibers that is transmitted so that you can can stream Real Madrid to Huntington Beach playing soccer. So this infrastructure already exists, and it's amazing that it works when you think about it. Now, two things. So first of all, the transmission in silica is very, very good. In fibers, it's 0.2 decibels for every kilometer. So 1,000 meters is 0.2 decibels of loss. And I should say that's only a particular wavelength, the telecom wavelength 5050. It's much worse. The wavelength that I'm used to working with, at 780, 795, it's as much as 10 decibels per kilometer, but 0.2 decibels, 10 to the minus 0.02 is the transmission there, which goes to about just shy of 96% of the light gets through for every kilometer. And that's great, right? You think you could just send all that information through, no problem. But anybody who's worked with exponential loss knows the tyranny of exponential loss, and that adds up quickly. So if you're going 6644 kilometers, that turns out to be, I did the math myself, 1,328 decibels of loss, or 10 to the minus 133 gets up. That's a very big number, right? So a Google, Googol, is 10 to the 100, and it's like a nearly unfathomably large number. This makes optical communication seem impossible at these distances. So photons about an electron volt. A watt of light is typically about 10 to the 19, 10 to the 20 photons per second. Megawatt, say 10 to the 23 photons per second. We said a megawatt, like a whole burning, insanely crazy amount of light through this fiber, and waited the age of the universe, not a single photon would get through. It's just too much loss. Yet, this thing works, and we didn't waste all our money on it. So how does that work? And the answer, the solution is a so-called repeater, the optical repeater. And how it works is that every so often, in this fiber 30 kilometers or so, you put an amplifier in the system. Called the classical repeater. There's semi-passive ones, such as this rubidium-doped fiber amplifier, and you get, say, 10 decibels of gain every 30 kilometers or so. So as the signal decays, it gets boosted and decays, and they're very cheap and easy to place in fibers, and they're placed along this cable here. And that's the only way we can transmit information over fibers for such a great distance. And we need to do this obviously with quantum states as well, because quantum states are far more unforgiving with loss than classical states. And we just found it'll take longer than the age of the universe to send a single photon through this fiber without amplifying. And herein lies a massive problem. If we try to actually build such a repeater that amplifies our quantum state, we're out of luck. So the problem really is that not only do we have to amplify a single photon, H photons, that's pretty easy actually, or a V photon. We need this device, which we're going to represent as a unitary operation that amplifies any arbitrary superposition of horizontal and vertical. And this turns out to be much more challenging. So let's make such a device. We'll have a unitary operation here that's going to take an arbitrary state, phi, which is alpha A plus beta B, and it's going to make a copy of it. We can just write that down, right? We can write down what comes out when we do that. So if I do that product here, scribble it all out, I get some term AA plus AB plus BA plus BB with some coefficients, and we're good. But if I also write that state and apply that unitary operator to the superposition directly, just from the linearity of this quantum mechanics, I find that state also must be alpha AA plus beta BB. So these two states are not the same in general. This can't be true in general. And we cannot clone an arbitrary state. We cannot amplify it. Another way of saying it, we can't have a noise-free amplification of an arbitrary state. This is known as the no cloning theorem. It's actually neat how it's such a simple proof for the case of a unitary, that it's like one or two. This was my second AI generated plot, by the way. So we're going to need something completely different. We're going to need a totally different technology called a quantum repeater in order to make this work. And that's a challenging thing. So it's going to have to work. We can't just amplify the system. It's going to have to work differently. And the basic idea of how this quantum repeater is going to work is Alice and Bob here want to share a Bell state, as we pointed out. We're going to share a Bell state so they can do entanglement swapping and distribute this network. And we have 500 or so kilometers of fiber. And just crunching a bit of numbers, we have an exponential loss. This is just Beer's law through the fiber. Primarily, sorry, from Rayleigh scattering. You can't get rid of that. So on average, if that's the probability of e to the minus L of transmitting, the way I like to think about it is we need 1 over that, or e to the alpha L number of attempts on average before it works. After that, we have a high, greater than 50% chance of it working. But if we just plug in the numbers here, say we have a gigabell pair per second source, and 0.2 decibels per kilometer corresponds to the non-decibel scale alpha, Goodness law of about 0.046 per kilometer. The loss is 10 to the minus 10. We're going to need about 10 to the 10 attempts in order for this to work. So even with our nearly unrealistically high 10 gigabell pair per second source, we're going to get an entangled bit every 10 seconds or so. So hardly a high bandwidth, right? So let's do something else. Let's put a node in between these two Alice and Bob here, and we'll call that a quantum repeater. And we're splitting the distance in 2, right? So now 250 kilometers between Alice and the quantum repeater, and another 250 from Bob. And I claim this is better, which is surprising at first, right? Because I still have a unit loss per length, and it still have to go through 500 kilometers of fiber total. But the idea is that each of these stations, including the quantum repeater, will have a quantum memory in it. So what I'll do is I'll try it to establish it not between Alice and Bob, but between Alice and the repeater and Bob. And eventually it's going to work. It's going to work with a much higher probability because of this exponential gain. L over 2 in the exponent means I get square root in the number of attempts needed here. And once that establishment between the quantum repeater, this intermediate station of Bob is established, I no longer try. I'm already done. And I'm just going to wait until the other one is established. And then I have established a quantum source between the two of them. And then I'll just do my entanglement swapping operation, right? After that. So plugging in the same numbers, even assuming I get a 25% chance of this working per station, I'm still getting 2,500 qubits per second instead of a qubit every 10 seconds. And this can be made much better by distributing the entanglement through more and more nodes. So the analogy I like to use for intuitively why this works is that if I give you 6 die, and you have to roll 6s every time, 6 to the 6th chance of doing it in once. But a quantum repeater, what allows you to do is you roll them all. Every time you get a 6, you put it aside, and now you have, say, 4 of them, and then you have to roll those, and you get to store all your 6s. So that's going to happen with much higher probability. That's the beauty of this idea, the simple idea of a quantum repeater. It makes things so easy, except the problem is that we do not have the technology to make these things work. So therefore, we do not have a quantum network yet. It's generic. We don't have these repeaters. It's a big challenge. So now that I've said that we don't have quantum networks, here's some example quantum networks. One of them is the Beijing-Shanghai, quantum backbone, which is a huge network in China with satellites and city-to-city links. There's also a practical one, Tokyo QKD network, which is functioning kind of proof of principle right now to distribute entanglement, as well as these up-and-coming ones. One is Stony Brook, and the one I'm most excited about that we heard 2 months or so ago about, which is KeySat, which is this the Canadian push that Thomas Genowin talked about in his talk. But the China, the Beijing, Shanghai quantum backbone is already in operation. It's distributing secure keys among itself without quantum repeaters. So that puzzled me when I first heard about it, because I've heard both of these things. And when you dig into why this is the case, it's not quite a quantum network that I described. Not quite quantum secure. It's using what's called a trusted repeater network. All right. So a trusted repeater network is what you do is you have these short distances where you do not trust the connection, and you can use short distance quantum key distribution to establish, for example, a secret key between yourself and the node. It is then held in these trusted nodes, converted to a classical signal, propagated amongst itself. And then when you get out of that trusted network, you convert it back to a quantum signal and distribute it that way. So the point is that you have some, government trusted nodes that cannot be hacked or so they say, that is transmitting the information. But the reason that we have these functioning quantum networks that you hear about, on the news, if they ever come up, is these are actually not fully quantum networks yet. Quantum key distribution, but classical distribution between quantum nodes. So the next step will have to be in making these. In the interest of time, we're going to keep going past some of these. I just want to talk about the big dream of this. There's like a lot of, in preparing for this talk, I'm like, I wonder if there's any popular books about this now. And it turns out there are. One of them is by John Dowling. It's a totally layperson book, which is really entertaining to read. John Dowling is a really funny guy who did a lot of the groundwork for quantum networks. Unfortunately, he passed away a couple of years ago. I had the pleasure of meeting him a few times, and he has a lot of great stories in this book. So I'll just point interested listeners to these two books. One is more technical, which is basically a textbook on how to build a quantum internet, and it's available PDF form online. It's done by Peter Rode on the internet, and many others. The one thing I do want to say about when you dig into these exciting applications, that things have to work really, really well. So for example, in the very long baseline interferometry work that I talked about, when you read that paper, it's a very beautifully written paper, and then you read some of the requirements, and they're very, like, you need about 100 gigabell pairs per second, and you have to have really good memory. So we're not quite there yet. Maybe even not tomorrow, but the day after tomorrow, we might be able to make Earth-sized telescopes to improve the resolution. Okay, so now that we've possibly motivated the work to contribute toward this quantum internet, I just want to spend the last part of the talk, the second part of the talk, talking about what we're actually doing to make it. So we have 3 projects on the go, all related to this, hopefully putting some of the pieces of the puzzle together. One of them is we're deploying we're looking at a field deployable quantum memory. We're looking at a way of converting light from the wavelength that is resonant to that memory to wavelengths that are conducive to long distance communication. And we're making a new source of squeezed light. So we'll go through all those 3 in a bit more detail. So first of all, benchmarking field deployable quantum memory. This quantum memory that we're looking at is based on a phenomenon known as electromagnetically induced transparency, which you may or may not have heard of. It's a neat trick. So if we have a 2-level atom and we're scanning a laser across it, across resonance, we'll get absorption, right? Accompanying absorption is always a change in dispersion, a steep dispersion curve. And that dispersion curve is very important because it determines the group velocity of the light. And I teach an optics course here at UVic, and my favorite, one of my favorite problems is to calculate the group velocity of a 2-level atom on resonance. And you find out that it is superluminal. It can be superluminal faster than the speed of light. So that's very puzzling, except for the fact that you get a huge amount of absorption around there, and it is absorbed in such a way that there's no superluminal communication possible. But electromagnetically induced transparency is a way of getting a very steep dispersion curve to allow you to have a group velocity different from light in the presence of transparency. And the way it works, we have these 3 atoms in these 3 levels of an atom in a so-called lambda configuration. We turn on an auxiliary field, and due to interference between these ground states to the excited state, we get a narrow transparency window. And we have a very steep dispersion curve right in the region where we get transparency. And that leads to a very small group velocity. We've used over 20 years ago now to slow light down to 17 meters a second and eventually even stop. So this is a way to create slow light and actually get the light out, but it's also a way to completely stop light. Because when light is traveling through there, and it's traveling at the speed of light in air, roughly, and then it goes into the slow light medium, it becomes compressed to the point where the entire pulse can fit inside the atom. And what the protocol is you adiabatically ramp down this transparency in a way that the eigenstate is maintained, and the group velocity goes to 0. You completely trap the light there. It is encoded in the coherence. The information of the pulse of light is encoded in a spin wave distributed across this cloud of atoms in such a way that it is completely preserved. And when the field is ramped back on, you get the light back. right? So this is the basis of a quantum memory, is to store information between these two ground states and retrieve it in a later time. Later, usually meaning a few hundred microseconds if it works very, very well. And the key parameters that we need to look at, again, are the efficiency, that is the probability that we get a photon out, the fidelity, what is the overlap between your arbitrary input state and your output state, and the amount of time we can store it for, because the atoms are typically banging into one another. So when I was started as a graduate student, I was working on one of these systems, one of these boxes from my old group, and it is mind-boggling to me now that you can buy these. So there's a company called QNet that is selling commercial quantum memories. I think the first of its kind. And the systems we made, as graduate students, were held together by like duct tape and a prayer. And it's amazing that you can get a repeatable rack-mounted device that will actually have a fiber optic in and a fiber optic out and can store memory. But one of the things we want to do is actually simulate a real-life, quantum node situation and just test its performance among a variety of settings. So just a few details on how this memory works. How might you store an actual qubit? So suppose I'm using a polarization encoding of my qubit. That is, I have a coherent superposition of H and V, and that's my qubit. I can use birefringent materials such as calcite, which will split the polarization up into two paths. It will go into the quantum memory, and it will be stored in different spatial locations of that quantum memory, and then be recombined upon retrieval. And it's using the hyperfine ground states of rubidium in order to form its three-level atom. So in real life, the level systems are never as nice as these idealized systems, but we can often approximate. And what they advertise is a fidelity of 95% at 160 microsecond storage time, which is actually fairly respectable, but a fairly low efficiency. And this might be a problem, something we're actually exploring, as to how this might limit our key rate if we're doing, say, a Bell state source to make quantum key distribution. So one of the things we look at room is why we would actually use this if the efficiency is so low. And the reason we're using an EIT memory is that it's so simple compared to a lot of systems, right? A lot of systems need cryogenics. Here you need a heat gun and a glass vapor cell and some laser diodes. And in principle, it works fine. Maybe a bit of magnetic shielding, but it's kind of, in my opinion, the only real candidate for cheap scaling of a quantum memory right now. So can we get around this limitation, right? The quantum repeater protocol that I talked about earlier kind of assumed that every time you wanted to store a photon, you got to store it and you got it back. What is this 7% efficiency due to all the imperfections in the cell? So one of the things we're doing, this is work in progress as we speak, as in like this week, we're looking at how our realistically measured efficiencies in such a memory will scale if we're trying to do a quantum key distribution application, right? So in this case, we're saying, let's split up our nodes A and B into n nodes, where n here is 1, 2, 3, or 4. And we can look at the advantage of having a repeater. So we make all the nodes click at the same time, or we do the trick where we have a quantum memory and we're allowed to hang on to it for some amount of time while the other ones catch up. If it takes longer than the coherence time to store the photon, we lose everything. But what we're seeing here with this plot is just the model using our realistic experimental parameters to see what the key rate that we can achieve with this quantum memory is. Now, this is not strategic. This is just the plot, the way it came out. The font is very small here, so I cannot hide this fact. This is a logarithmic scale, and the key rate we're predicting over 80 kilometers is on the order of 10 to the minus 3 per second. So 1 every 1,000 seconds or 13 minutes or something like that. Quite pessimistic. And what we've kind of found here is that we're going to need to increase the efficiency of these memories. And there's protocols and ways of doing this with different pulse shaping, but it's not going to work as a suitable scalable quantum node as is. The fidelity is very good, but we're going to be heavily key rate limited by these realistic quantum memory effects. Okay. E2, I want to get to this part too, because it's also very exciting, is a way to transmit information through an optical fiber. That EIT memory that we talked about before, it naturally works at one of the hyperfine lines of electromagnetic transparency, either 780 or 795. And if we put that light, we store that light, retrieve it, send it through a fiber, that is exactly where we said we had 10 decibels per kilometer of loss. It's not going to work at all. So that 10 decibels per kilometer of loss means that 1 kilometer of rubidium wavelength fiber is like 50 kilometers of telecom. We just we can't send information this way reliably. Loss will actually kill us. What we can do is either try to find a new protocol, a new set of atoms or artificial atoms that can work at 1550, or try to up or down convert photons to an appropriate wavelength. And that's the thing we're taking a stab at here, but it has to do so in a way that preserves the quantum state. So we're going to use a technology known as four-wave mixing in the so-called diamond configuration. This is a bit misleading because diamond is also used as a material for quantum memories. This is just the shape of the diagrams that are being used. So rubidium is not just the 780 and 795 nanometer wavelengths. There's a number of dipole allowed transitions, and they can form these so-called diamond schemes. We're looking at one of these schemes to coherently transform between the two wavelengths 1550 and 795. We've done some kind of preliminary simulations. We're trying to obtain the lasers for these now. But there's already been some work using this scheme in the so-called O-band of telecom, 1324 nanometers, and the C-band here. So when you actually look at these simulations, this experimental work very recently, last year or two, is starting to show some promise here. A key figure is we need a very, very high optical depth for this. We need a large probability of interacting photon with material, and that's actually hard to do. You can do so in a vapor cell and then heat it up and other processes happen. You can use a magneto-optical trap. And right now we're just trying to build a system that has a sufficiently high optical depth. All right, last experiment I want to talk about. By the way, are we pretty much out of time? Or yeah. Okay, so I'll just show you in a nutshell and leave it up to questions after that. We can also make four-wave mixing another way to make squeeze light. Now, anybody who was at Quantum Day last year already heard me talk about it. If not, this coming out, so I don't have to go into all the detail because everybody, I'm assuming in the audience, has a photographic memory and attended everything. But the long and short of it is that these processes allow a biphoton source to be created. We've done some work of this to create a squeezed state of light. The very, very condensed version of this is we're coherently scattering two photons into two separate modes in a way that preserves momentum and energy. We've already done a lot of work with this. This is all old news, so I won't go through this. We'll talk about what we're doing tomorrow instead of this work, which is creating single photons and shaping them. We're going to use it to create a single mode of squeeze state so that we can interact it with these quantum memories and store a squeeze state in the quantum memory, retrieve it, and then we get a true blue test of how capable this quantum memory is in actually retrieving a quantum state. So this leads to our grand vision of what we want to do over the next 10 years. We're hopefully end at a single digit number, but who knows? We want to take that source, connect it to our conversion, put it to a quantum memory, and really test the node, the quantum internet node that we're actually making. So a bit of a rush on those last two slides, but this is the grand vision. Check back in 2 years or so, optimistic, 2 or 3 years, and we'll see how far this is going. I just want to conclude by thanking all of the people that contributed to this. In case you're wondering why there's so many names, we have a lot of great undergraduates here, and many of these undergraduates worked really hard throughout the summer to build this, have built these experiments up over time. So thank you for your attention. I'll leave it at that, and of course, open to questions, and get in touch with email if you want to chat about what opportunities or have any further questions. Thanks so much.
Thank you for that excellent talk. That was very nice. Very good overview. We have a hard cutoff, a couple of minutes, so we have to cut this a little bit short, but we have time for maybe 1 or 2 questions. You're going to this thing.
Yeah.
Yeah, so we need to maybe have
I can be
4 minutes.
That is like incentivizing no one to want to ask questions.
Yeah, sorry, no, it's important.
Yeah, yeah. Planned everything perfectly.
You killed it. There was a slide, maybe back, several slides, maybe about 15 slides. And you were mentioning that, it had something to do with the repeaters. Um, you were mentioning that it was very, very difficult to put these together. Oh, no, actually, I do have another one. Okay, this whole, method of distributing entanglement is required. It's sort of like a tree. You have to have central nodes that sort of distribute out to other nodes. There are these other proposals out there for tripartite entanglement, where you have coupled spins, singlet pairs, for example, between Alice, Bob, and Charlie, or whatever name you used. Are there feasible experimental proposals to do things sort of more equitably, or do you need sort of the top down?
Tripartite, or a lot of experience with the so-called GHZ states. Familiar with? Yeah. And yeah, you get an advantage, an even better advantage, for example, for the very long baseline geometry, you can get a better advantage with GHZ states. Scaled with 1 over, or so-called noon states as well, n states here, 0 states there, or vice versa. So the qubits are kind of the simplest. Bell states are the kind of the simplest ones, but there are other states, yeah, where you can get slightly better scaling.
What's better from the experimental side?
I'm a Bell source for sure. Much easier it's very difficult to make these high dimensional entangled states, in my opinion. Anybody has a better way of saying it?
And you said sort of a throwaway comment on one slide, and I wanted you to expand on it a little bit. It was, maybe if you just go back a couple of slides. That was really interesting. It was like in the lower right. If you just keep flipping through, I'm sure.
Oh, it might have been like.
Oh, it might have been on the error detection, error correction, or some statement that you said, and I was like, oh, I really want to follow up on that. So, cool.
Yeah. The answer is 42.
I suppose, yeah. Well, do we have any other questions from?
I can't do the chat. Look, there's anything in the chat.
Hi, Andreas. So there's a question from SF I want to ask. In that EIT quantum memory, so how do you know the memory has absorbed a photon?
So the EIT quantum memory has to work, and this is kind of another elephant in the room, deterministically. So either null detection on the other side, or so I'm just get that slide here, if not good enough, null detection, or it just has to have a very, very high efficiency. So this efficiency here, we have to select afterwards. There are other protocols, such as the so-called DLCZ, Dwarm-Lukin-Zoller protocol, where you do get an ancilla for, you can detect a scattering event that shows that you've stored a single memory. But the EIT itself, the goal is just to have it, the optical depth high enough that you can get a sufficiently high efficiency that you are getting it every time, which is clearly not the case now. It is non-heralded, which is a big problem if it stays with the efficiency at 7%.
Okay.
Thank you. Thank you.
Well, super. So I'm sorry that we don't have the remaining 5 minutes for more questions. I'm sure that Andrew would be happy to take any questions if you want to send him an email, or catch him maybe at Research Day. You'll be there. Yeah. Fantastic. So let's thank the speaker one more time, and thank you, everyone. Sorry again, we have to go.